Hello, good morning. Welcome to the Green Room. My name is Samuel Budede. Today we'll be looking at decarbonizing the industrial sector using CCU technology. Our project objective. At current, the CO2 emission, if not controlled, will lead to an increase of about 3% or more to the global temperature above pre-industrial level. More than 20% of our greenhouse gases globally is generated from industrial activities, meaning from the exploratory phase to the processing phase and the consumer. All these sectors generate releases greenhouse gases to the atmosphere. So there is a great opportunity to utilize the invention of CCU technology to reduce the industrial carbon footprint and also convert the CO2 to a usable fuel such as methanol. Looking at the global demand currently, we see that this oil and gas play a major role in our global world, followed by a non-renewable sources, the coal, and we have also renewable alongside. So what our desire is to move from what it is to a net zero emission, meaning that we are planning to reduce the use of oil and gas, the demand of oil and gas, and improve that of hydrogen and other renewable sources. And how can we do that? We have to make use of the CCU. Why do we have to use the CCU? Currently, we get to see from a gas power plant that emissions are being generated from a gas power turbine, for example, that CO2 and nitrogen are released to the atmosphere, and as a result, it causes more harm to our climate. Now, why do we need to do this? The CCU technology is a power to liquids, or we could call it a power to gas also, which enable us and also convert the CO2 captured to a usable synthesized fuel. And this CO2 combines with hydrogen alongside with the aid of Fischer-Tropsch or methanology to produce methanol, aviation fuel, and other usable products. Now, this tells us that CCU technology is a bridge to a sustainable energy future or renewable energy future. What is the procedure for the CCU technology? We have three different phases for the CCU technology. Phase 1 looks at the CO2 extraction. Phase 2 will be looking at the hydrogen extraction, and phase 3 looks at the hydrogenation to methanol. Now let's take a look at the phase 1. The gas feed comes into play, moving into the tank, and from there, with the aid of the scrubber, it strip off every form of liquid before going into the combustion chamber. At the combustion chamber, we know that there is a difference between this combustion chamber with this combustion chamber. Thanks to Randy Allen, for the Allen cycle, he generated the design. Because of the supercritical heat state, the CO2 can also move along with the heat to the turbine. And after this process, our hot CO2 can be extracted at the other end, thereby reducing or eliminating the flaring or release of CO2 to the atmosphere. Now, this is a closed loop system. The hot CO2 moves into the heat exchanger, and after the heat exchanger, it cools down. The heat exchanger cools the temperature of the CO2, that's the carbon monoxide. And the cool carbon monoxide split into two. We have little of it moving into the centrifuge pump, the compressor, and also goes to support combustion. The remaining goes into the absorber, and at the absorber section, the amide comes into play, stripping extracting the CO2, and after the CO2, nitrogen is released or collected at the other end. The amide and also the CO2 moves into the deabsorber, and the amide is being extracted, thereby releasing CO2 of 90 to 95% pure. Now we look at the phase two. We could use the renewable energy to generate electricity for the electrolysis process, or we can make use of uh, electricity generated from the CO2 extraction process. Anyway, we can still do that. And now this using renewable energy source, we get to see that in the electrolysis process, hydrogen and oxygen are being extracted. This hydrogen can be will be collected and the oxygen can be released to the atmosphere to support the climatic condition, or can be put into bottles, cylinders for medical purposes. It has various uses. Now we look at the ultimate stage, which is the phase 3 stage. The phase 3 stage looks at hydrogenation to methanol. Now the hydrogen comes into its tank from the phase 2, and based on the pressure of 400 bars, it moves into the buffer volume. The buffer volume steps down the pressure and reduces it down to 350 to about 300 bars. Because of this, we have a CO2 coming, joining the stream from the extraction of phase 1. It joins the stream at the gauge section. After the gauge, it joins the hydrogen stream. Now, moving alongside these two fluids joins the mass flow controller. The mass flow controller does the purpose of regulating the flow of the mixed fluid to the reactor. At the reactor section, we have the proper reaction of this fluid, and below we could see the equation of this reaction. After this is done, we have a methanol and also water of about 60 to 40 ratios. That we have 60% of methanol and 40% of water being generated. With the aid of a backflow regulator regulating the flow of this fluid to the gas chromatography. A gas chromatography can be used, or we can make use of, instead of a gas chromatograph, we can use a distillation column to properly separate the methanol from the water. Since water is more dense than methanol, we could use a distillation column, drain out the water, and also get our methanol. Or we could use a gas chromatography, further separating this methanol into olefins, lower olefins, and there are various uses of this, greater benefits of this process. One, we are going to definitely do generate what a lot of benefit, because the synthetic liquid fuel can be blended with a gasoline and also can be used as fuel cells. It can be used directly, and also ultimately our desire of reducing the CO2 emission will be actualized. Significant reduction. Now our CCU technology comes in greater hands for the aviation industry. As we all know, pollution from the aviation sector cannot be controlled. With the aid of the CCU, that's the methanol, we can thereby eliminate this. From about approximately 593 tons of CO2 from the aviation sector, UK, for example, will be having a minimum approximately zero emission from this, because the methanol burns with a blue flame without any emission being generated. Little or no emission is generated from the aid of methanol combustion. Now, this tells us that we will be able to actualize our desire of meeting our Paris Agreement and also generate revenue alongside. Because of the cost of methanol, a ton of methanol is about 450 tons to about 600 tons. $450 per ton to about 650 or $660 per ton, depending on the country. For example, a plant setup can cost about $81 million to set up. And then with this capturing process, we can be able to actualize and also recover the cost of setup within a period of 5 to 10 years, depending on our plant capacity. With the understanding that, yes, for example, 60 kilotons of CO2 will generate about 42 kilotons of methanol, and this alongside will generate about $18.9 million as revenue. This calculation was done for a rate of $450 per ton. This tells us that we cannot just only decarbonize the industrial sector, but we can also generate revenue and also secure our climate. References, I would like to give kudos to Carbon Recycling International for their great contribution towards this research, towards this, and also I would like to give kudos to um, Ezekiel Hout Elisha and also Akinsola Audu for their contributions in this process, alongside every carbon capturing plant out there for their great contribution to our global world. Thank you very much.